Hey everyone, welcome back to Miss E's Math, where we make upper level math make sense. In today's video, we're diving into the calculus of parametric equations, a powerful tool in both math and physics. You'll learn how to find the derivative of y with respect to x in terms of a parametric equation, calculate arc length in parametric form, and find the area of a surface of revolution. Grab your notes and calculators because we're about to unlock some cool applications of derivatives and integrals with parametric curves. Let's start by finding the derivative of parametric curves. So our derivative formula, if we want to find the derivative of y with respect to x, I take the derivative of y with respect to t divided by the derivative of x with respect to t, assuming our denominator is not equal to 0. Let's find the derivative of y with respect to x if x is equal to the sine of t and y is equal to cosine of t. So let's first start by using our formula that the derivative of y with respect to x is equal to the derivative with respect to t of cosine t divided by the derivative with respect to t of sine of t. So the derivative of cosine of t with respect to t is equal to negative sine t, and the derivative of sine of t with respect to t is equal to cosine t. So negative sine t over cosine t is equal to negative tangent t. And that's how you find the derivative using a parametric curve. For our next example, we're going to find the slope and concavity at a given point. So I notice that I am given the point in terms of x and y, but since I'm given parametric equations, I need to find the t value when x is equal to 2 and y is equal to 3. So that's going to be our first step so that I can apply this information to my parametric equation. Now you can choose whichever equation, either the x equal equation, the y equal equation, doesn't matter which one. I'm going to choose the x equal equation. I'm going to let x equal the square root of t, or 2 is equal to the square root of t. Squaring each side, I get t is equal to 4. Now if you had chose the y equation, you would have also got t is equal to 4. So that's our first point of interest. Now the next step is to find the slope of our parametric curve. We call the derivative of y with respect to x is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. Recall that x is equal to the square root of t, or x is equal to t to the 1/2, while y is equal to 1/4 times t squared minus 4, or y is equal to 1/4 t squared minus 1. Now let's start by finding the derivative of y with respect to x. That's going to be equal to the derivative with respect to t of our y function, which is 1/4 t squared minus 1, and the derivative divided by the derivative with respect to t of t to the 1/2. So let's differentiate that numerator, and that would give us 1/2 t, and differentiating the denominator gives us 1/2 t to the negative 1/2. All right, let's simplify this down, and we end up that t is equal t to the 3/2 is our dy dt. Converting them back into radical form, that'll be equal to the square root of t cubed. Our next step is to find the slope at the given point. And the given point, remember, is when x is 2 and y is 3, or when t is equal to 4, because we figured that out in step 1. So we want to find our slope would be replacing t with 4, so that'd be the square root of t cubed, which simplifies to 4, the square root of 4, or 4 times 2, which is equal to 8. Before moving on, let's define higher order derivatives in parametric form. So our second derivative of y with respect to x is equal to our derivative with respect to t of dy dt, which we found, that's our first derivative, divided by dx dt. Our third derivative of y with respect to x is equal to our second derivative divided by dx dt. Looking back at our last example, now let's do the second part where we find the concavity at the given point. So I've written some important information we already figured out in part A of this. We found our derivative of y with respect to t, and we also found our derivative of x with respect to t. So in order to find concavity, we recall that concavity is the second derivative of y with respect to x. And we also just learned that that is equal to the derivative with respect to t of our first derivative, dy dx, over dx dt. So in this case, our second derivative is going to be the derivative with respect to t of t to the 3/2 divided by our dx dt, which is 1/2 t to the negative 1/2. So all I need to actually do is differentiate t to the 3 halves, which will give us 3 halves t to the 1 half, and that's divided by our 1/2 t to the negative 1/2. Simplifying this down, we get 3 halves over 1/2 is equal to 3. T to the 1/2 divided by t to the negative 1/2, we subtract our exponents or actually add them to get t. So our second derivative is simply 3t. Now we wanted to find the concavity at the point 2,3. So what we need to do is evaluate at the point 2,3 or when t is equal to 4. So let's plug into our second derivative, evaluate it at t equals 4, and that'll give us 3 times 4, which is 12. So I know the concavity at this point is 12, which is a positive number. And recalling from earlier calculus classes, when the second derivative is positive, our function is concave up. So we know our graph is concave upward at the point 2,3. For example 3, we want to find the equations of our tangent lines at the point 0,2. So our first step is to find the t value for which the point has an x value of 0 and a y value of 2. So again, remember I can plug in the 0 into our x function or the 2 into our y function. It really doesn't matter which one you choose. But because the y equation only has one t variable, I'm thinking it's going to be easier to substitute into that. So I'm going to use my y equation. And I'm going to replace the y with 2. And I'm going to solve this equation for t, starting by subtracting 2 from each side to get a 0 is equal to negative pi times cosine of t, then dividing each side by negative pi to get 0 is equal to cosine of t. Then ask myself what angle has a cosine of 0 degrees, and that would be plus or minus pi over 2. Next, let's find our slope, or derivative of y with respect to x, which we call is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. Remember, x is equal to 2t minus pi sine of t. So we need to find the derivative of x with respect to t. And that's going to give us 2 minus pi cosine of t. And also recall that y is equal to 2 minus pi cosine of t. And the derivative of y with respect to t is going to give us pi sine t. Plug in those two derivatives into our formula. We have a derivative of y with respect to x is equal to pi sine t divided by 2 minus t sine t. Now, next thing I'm going to do is I'm going to evaluate this derivative at t is equal to negative 1/2 and at t is equal to 1/2. I'm just going to throw it up here, and so you might want to pause the video and make sure that you can get this information and follow the steps I just did. Now that I know my slope at t is equal to negative 1/2 is negative pi over 2, and at t is equal to 1/2 is equal to pi over 2, we're going to find our equation of our tangent line. To do this, I'm going to use my point slope formula, or y minus y1 is equal to m times x minus x1, where x1 and y1 is our given point, 0, 2, and our slope is what we just found in the last step. So at time t is equal to negative pi over 2, our slope is equal to negative pi over 2, and our point is 0, 2. Plug that into our point slope formula, we get y minus 2 is equal to negative pi over 2 times x minus 0, which will simplify down to y minus 2 is equal to negative pi over 2x, or y is equal to negative pi over 2x plus 2. Let's repeat this process for t is equal to pi over 2 and a slope of pi over 2 at the point 0, 2. And our second equation of our tangent line is y is equal to pi over 2x plus 2. And we've answered the question. We found the two equations of the tangent lines of where this function crosses over itself. Next calculus operation for parametric curves is looking at the arc length in parametric form. So this formula should be very familiar when we learned arc length earlier in the school year. So arc length is equal to the integral of a to b of the square root of our derivative of x with respect to t squared plus our derivative of y with respect to t squared dt. So looking at this example here, a circle of radius 1 rolls around the circumference of a larger circle of radius 4, as shown in our figure to the right here. We are given a parametric curve, x and y. We want to find the distance traveled by the point in one complete trip around the larger circle. Now, in sort of doing the complete from 0 to 2 pi, I'm going to see the symmetry in this picture, and I'm only going to evaluate this from 0 to pi over 2 and times my answer by 4 for the 4 different quadrants. And it'll just make life a little bit easier. So our t is going to start at 0 and go to pi over 2. Our distance traveled is equal to our arc length, and I'm going to use our arc length formula of the integral of a to b of the square root of our derivative of x with respect to t squared plus our derivative of y with respect to t squared dt. So I want to times this by 4 for each quadrant. And so I need to figure out my derivative of x with respect to t first, since t is equal to 5 cosine t minus cosine 5t. That derivative is equal to negative 5 sine t plus 5 sine of 5t. And our y function, when I take the derivative of y with respect to t, I'm going to get 5 cosine t minus 5 cosine 5t. Okay, I want to substitute that into my arc length formula, remembering to take our x derivative with respect to t and square it. And the same thing to our y derivative with respect to t, we're going to square it. Okay, so I'm going to do the full method. I'm going to take my negative 5 sine t plus 5 sine 5t and square that. Well, after I square it, I end up with 25 sine squared t minus 50 sine t sine 5t plus 25 sine squared 5t. Next, I'm going to take my dy dt and square it. And I end up with 25 cosine squared t minus 50 cosine t cosine 5t plus 25 cosine squared 5t. That's all underneath the square root, and I'm taking this integral from 0 to pi over 2 dt. We're going to have to do a lot of simplifying to evaluate this integral. I'm going to start by putting terms together that look like trig identities that I know. For example, I'm going to take this 25 sine squared t and add that to my 25 cosine squared t, put those together. Likewise, I'm going to take the 25 sine squared of 5t plus the 25 cosine squared of 5t and put those together. Lastly, I'm going to take the negative 50 sine t sine 5t and put it with the negative 50 cosine t cosine 5t. Now I'm going to choose to write this with the, write it as negative 50 sine 5t sine t, and then minus 50 cosine 5t cosine t, so that this last term better fits our difference formula for cosine. Continue to work on simplifying. We're going to factor out the GCF of 25 from that first group of parentheses to get 25 times sine squared t plus cosine squared t. And I'm going to do the same thing, factor out the GCF of 25 from the second set of parentheses to get sine squared 5t plus cosine squared 5t. And then on this one, I'm just going to factor out the negative 50. And I'm going to write my cosine term first, so it better matches the formula I'm used to with our the difference formula for cosine. Okay, I'm ready to start my actually simplifying here. So first thing I'm going to do is I'm going to use my trig identities, replace sine squared t plus cosine squared t with 1, and sine squared of 5t plus cosine squared of 5t with 1. And so that gives us 25 plus 25, which is 50, minus my 50, and then I'm going to replace this last set of parentheses here with our difference formula for cosine, which is cosine of 5t minus t. All right, and our next simplifying down, still working underneath the radical, I can factor out our GCF of those two terms of 50. And so I have the square root of 50 times 1 minus cosine of 4t dt. Now I'm going to break this up and take the square root of 50 times the square root of 1 minus cosine of 4t dt. And the square root of 50 is 25 times 2, or 5 the square root of 2. And then I still have underneath the square root 1 minus cosine of 4t. Recognizing that cosine of 4t is the double angle of 2t, so I can replace that with one of my double angle formulas for cosine. I'm going to choose the 1 minus 2 sine squared of 2t. And then distributing the 2 to each of those, I end up with 2 minus 2 plus 4 sine squared of 2t, which simplifies down. 2 minus 2 cancels out. And I'm left with the underneath the square root of 4 sine squared of 2t. And of course the square root of 4 is just 2, and the square root of sine squared 2t is sine 2t. So I've gotten rid of the square root finally from my integral, which is going to make, well, now we're going to be ready to integrate. All I'm going to do is use u sub to integrate this, letting u is equal to 2t and du equal to 2 dt. Or you could say that dt is equal to du divided by 2. And so I have our arc length is 20 times our integral from 0 to pi over 2, with t is equal to 0 and t is equal to pi over 2 of 2 sine u du over 2. The 2's cancel each other out. So arc length is equal to 20 times the integral of t equals 0 to t equals pi over 2 of sine of u du. Doing the integral of that, integral of sine is negative cosine, so I have negative 20 cosine of u, evaluate it from t equals 0 to t equals pi over 2. Going back to my t variable, I have the arc length is equal to 20 cosine of 2t, evaluate it from 0 to pi over 2. Substituting in pi over 2 in place of t, I get negative 20 cosine of pi. And then minus a negative, so it becomes plus 20 cosine of 0. Using my unit circle, we know the cosine of pi is equal to negative 1. And I know the cosine of 0 is equal to 1. So we know our arc length has to be 40. That is, the distance traveled by the point in one complete trip about the larger circle would be 40. Lastly, we're going to learn how to find the area of a surface of revolution using parametric form. And so we have two equations to look at depending on if we're rotating around the x-axis or the y-axis. Surface area is going to be equal to 2 pi times the integral from a to b of our g of t, which is our y function, times by our arc length if we're revolving around the x-axis, and if we're revolving around the y-axis, it's going to be 2 pi times the integral from a to b of our x function times our arc length. Applying our area of a surface of revolution equation formula to this equation, we have a circle x squared plus y squared equals 9 from 3, 0 to 3 halves, comma, 3 the square root of 3 over 2. To find the area of the surface of revolution, we first need to change our rectangular equation x squared plus y squared equals 9 into parametric form. And so since we recognize that this is an equation of a circle, so x is equal to r cosine theta, or t, and y is equal to r sine t. So since r is 3, we have our equation, our parameterized equation is going to be x equals 3 cosine t and y is equal to 3 sine t. Now that we know our parametric equation, we need to figure out time t at the point 3, 0 and time t at the point 3 halves and 3 the square root of 3 over 2. So again, I'm going to choose to plug this into either my x equation or my y equation. It really doesn't matter which one. You will get the same answer. I'm going to choose to plug it into our x equation. So I'm going to let 3 equal our x, and so I'll have 3 equals 3 cosine of t. Solving for t, I get t equals 0. Next, I'm going to find the t value for our second point, the 3/2, the comma 3, the square root of 3 over 2. Again, I'm going to choose the x variable mainly because 3/2 is much neater than 3, the square root of 3 over 2. Solving for cosine of t, I get 1/2 is equal to cosine of t, so the angle whose cosine is 1/2 is pi over 3. So I know my integral is going to be from 0 to pi over 3. And so I'm going to now plug this information into my area formula for areas of revolution. Now the problem said that we're revolving around the x-axis, so I'm going to use that first formula, which is equal to 2 pi times the integral from a to b of g of t times the square root of f prime of evaluated at t squared plus g prime of t quantity squared dt. So this is that first one for revolving around the x-axis. So I'm timesing my arc length by my y function inside my integral. So let's plug in the information we know. Well, we know our a we just found to be 0 and our b pi over 3. I know my g of t function, which is my y function that I found earlier. So recall that we found x to be equal to 3 cosine t. So let's go ahead and find the derivative of x with respect to t, which is going to be negative 3 sine t. And we also found earlier that y is equal to 3 sine t, and the derivative of y with respect to t is going to be 3 cosine t. So let's plug that into this formula. So in place of g of t, I'm going to plug in 3 sine t. And then the square root, in place are our derivative of our x function with respect to t, dy dx dt. I'm going to plug in this negative 3 sine t, and then we're going to square that, plus our derivative of y with respect to t, which is 3 cosine t in quantity squared. Okay, again, we're going to start by simplifying underneath the radical so that we can evaluate this integral. Well, negative 3 sine t quantity squared is just going to be 9 sine squared t. And 3 cosine t quantity squared is equal to 9 cosine squared t. I can factor out the GCF of 9, and that leaves me underneath the radical of 9 times the square root, 9 times sine squared t plus cosine squared t. That's the Pythagorean identity. We know that sine squared t plus cosine squared t is equal to 1. And so I have underneath the radical square root of 9 times 1, which is just the square root of 9, which is simply 3. And so I can take that 3 times it by the other 3 to equal out underneath my integral of 9 cosine t dt. Now I'm going to factor out that constant 9, and 9 times 2 pi is going to give me 18 pi as my coefficient outside my integral. And all I have to do is figure out the integral from 0 to pi over 3 of sine of t dt. That's simplified pretty easily. So the integral of sine we know to be negative cosine t, evaluated from 0 to pi over 3. So I have negative 18t times by cosine of pi over 3 minus cosine of 0. I know from my unit circle the cosine of pi over 3 is 1/2, and the cosine of 0 is 1. And so I end up with a final answer for 9 pi. So that tells us the area of the surface formed by revolving our arc of C around the x-axis is simply 9 pi. Now you know how to apply calculus to parametric form equations, and we learned quite a bit in this video. We learned about the derivative of parametric form. Here's our derivative formulas for our first, second, and third derivative of y with respect to x when it's written in parametric form. Then we also found our arc length in parametric form, which is simply just an integral from a to b of the square root of our derivative of x with respect to t, quantity squared, plus our derivative of y with respect to t, quantity squared. And then we learned how to find the area of surface of revolution in parametric form. If we're revolving around the x-axis, we take 2 pi times the integral of our y function times by our arc length. If we're revolving around our y-axis, we take 2 pi times the integral from a to b of our x function times our arc length. If this helped you, don't forget to like this video, share it with your classmates, subscribe to Miss E's Math for more easy to follow calculus lessons, and comment below with your questions or what topics you want to see next.